Okay, we are live now.
Shall I start?
I think he left. I mean, he joined back.
Oh. Okay.
So there was some. Can you see the slide now?
Yes. Okay, so good afternoon again. So we are meeting again for a very interesting talk by Professor Bibekananda Maji from IIT Indore. So Vivek did his bachelor's from Ramakrishna Mission Belur College, and then followed by an MSc in mathematics from IIT Bombay, PhD in Harishchandra Research Institute, after which he joined IIT Gandhinagar to work with me. We had a fabulous 3-year period working on several projects, interesting ones. And then he joined IIT Indore as an assistant professor of mathematics, where he is right now. And he'll be talking today on Ramanujan's formula for zeta half and zeta 20%. Over to you, Vivek.
Thank you so much for your kind words. Yeah. So first, I'd like to thank organizers for the invitation. So today I'll be speaking on Ramanujan's formula for zeta half and zeta 2m plus 1. So this is a joint work with Anusri Gupta. Recently, she has completed her MSc from IIT Indore. Okay, so let me begin with well-known Riemann zeta function. Riemann.
Vivek, just a suggestion, if you can click on that arrow on the right so that you can make it full screen.
Okay. So it is not a full screen.
I mean, we see that bar on the right. I mean, that's fine. But if you can, if it goes, that would be better.
So, okay.
Yeah.
Now it is fine?
Okay. Yes.
Okay, thank you. So Riemann, in his seminal paper, he studied this series 1 by n to the power s, and which is defined for real part of s greater than 1. It is absolutely convergence in this domain, and it is uniformly convergence also in any compact subset of this domain. So therefore, it defines an analytic function in this domain. So in this paper, Riemann also proved that it can be analytically continued to the whole complex plane except at s equals to 1. And he proved this beautiful functional equation, which is, you can see that symmetric if you just replace s by 1 minus s. So if you see the image of this, it will be symmetric about the half line, real part of s equals to half line. And all of you know that he conjectured, which is known as Riemann hypothesis, that all the non-trivial zeros of this Riemann zeta function lie on real part of s equals to half line. Okay, so before Riemann, Euler studied this series, but he studied only for at even argument. Okay, so series 1 by summation 1 by n to the power 2m, where m is natural number, he has expressed in terms of like pi and Bernoulli number. And one can show that Bernoulli numbers, they satisfy our recurrence relation. And from there, one can easily prove that all Bernoulli numbers are rational numbers. And if we assume that the pi is transcendental number, so which is proved by Lindemann, then one can easily say that all even zeta values are transcendental. And even zeta values they are related to each other. Like one can, like zeta 2 is pi square by 6, zeta 4 is pi to the power 4 by 90. So in that sense, zeta 2 and zeta 4, they have some algebraic relation. Now, natural question is that once we know that all even zeta values are transcendental, the natural question is that what can you say about algebraic nature of odd zeta values? Now, there is a folklore conjecture. People believe that pi, zeta 3, zeta 5, and other odd zeta values, they do not satisfy any non-zero polynomial with rational coefficient. And that implies that all odd zeta values must be transcendental, but which is still a conjecture. Now, let's see what is known till today. In 1979, Roger Apery, a French mathematician, proved that a zeta 3 is an irrational number. And he used this formula. Now, by definition of the Riemann zeta function, we know that zeta 3 is summation 1 by n cube. But then what is the importance of this formula? This series converges rapidly. Okay, this, of course, this formula has really, it was really important for him to prove this. Like this formula, using this formula only, he was able to prove that zeta 3 is an irrational number. And you can see in his gravestone also, it is mentioned that zeta 3 is not equals to p by q. Okay. Now, at the beginning, like mathematician, when he proposed this proof, mathematician didn't believe his proof. But later, Henry Cohen and Lenstra and Alfred, I forgot the full name. So Alfred wrote a nice paper explaining Apery's proof. Then a mathematician believed that the proof is, Roger's proof is correct. But then after that, people are trying to extend the similar proof for zeta 5, but it is quite challenging. Still, we are not able to prove that zeta 5 is irrational. Okay. So then Rival and Ball and Rival, first Rival wrote a paper, then Ball and Rival together they wrote a paper, proved that there exist infinitely many odd zeta values which are irrational. Mainly they have proved, like if you consider the field generated by Q with this odd zeta values, then the extension, the degree of the extension is like big, lower bound is constant times log n. Okay, like if you consider n odd zeta values, and if it's when n tends to infinity, then the degree is going to infinity. So therefore, from there, one can say that there will be infinitely many odd zeta values which are irrational. But if you want to say whether, particularly whether odd zeta value, like for example, if you want to say whether zeta 5 or zeta 7 is irrational or not, that we cannot say from their result. Currently, the best result in this area is due to Vadim Zudilin. It's the result is saying that at least one of zeta 5, zeta 7, zeta 9, and zeta 11 is irrational. So Zudilin also gave an elementary proof of the Apery's theorem. And later, actually, Yuri Nesterenko, other mathematician, also gave elementary. Boykers gave a proof of Apery's theorem. I think one of the organizers is also expert in this area, in Apery's Krishnan. Okay. Okay, now let me talk about Lambert series. Lambert series are defined like this: a series an q to the power n by 1 minus q to the power n, where an is arithmetic function and q is some complex number with mod q is less than 1. Now, if we consider q is exponential minus z with real part of z is greater than 0, then you immediately get this form. Now, generalized Lambert series, here we are inserting one more extra variable, capital N, which is like this arithmetic function also there is capital N, and in the denominator exponential n to the power capital N times z minus 1. Now, one may wonder that why we are inserting this extra variable. So soon we'll see the importance of this extra variable, capital N. Okay, now let me talk about Ramanujan's formula for odd zeta values. Ramanujan, before going to England, in his second notebook, he noted down this beautiful formula for odd zeta values. So it states that let alpha and beta be two positive real number with alpha beta equals to pi square, and m is any non-zero integer, then this identity holds. Now, at the beginning, this formula may look a little complicated, but if you see closely, then you can see the beauty of this formula. So see, in the left-hand side, a single odd zeta value is present and one Lambert series. In the right-hand side, in this also same odd zeta values and the Lambert series is present, which is just, so these two expressions are symmetric in alpha beta. If you just replace alpha by beta, then you will get this expression. Only this -1 whole to the power minus m is present. And this is a finite sum involving Bernoulli numbers. Okay, so here one important thing is that the convention is, since I have mentioned that m is a non-zero integer, so m can be negative. So therefore m plus 1, when m plus 1 is less than 0, then we consider that this sum is a zero sum. Okay, so that is the convention. Okay, so as I said that Ramanujan mentioned this in his second notebook, as well as this can be found in lost notebook in this set. Okay, let's see immediate implication of Ramanujan's formula. So here, if we put m is even number and alpha beta equals to pi, then these two terms will get cancelled, and then immediately we'll get the sum of the Bernoulli numbers will be 0 when m is positive even number. But when, if you consider m is a negative, odd positive number, and alpha beta both are pi, in that case, we'll get this result of large. So here, m is a positive, odd positive integer. Okay. Now, if you see this right-hand side expression, finite sum involving Bernoulli number, since all Bernoulli numbers are rational numbers, so this finite sum is a rational number, and is pi to some power of pi is there. So pi is transcendental number. So therefore, this right-hand side expression is a transcendental number. And this series is a very rapidly convergent series, because in the denominator exponential function is there. So that's why people often say that this zeta 4k plus 3, since m is odd, so zeta 4k plus 3 numbers are almost transcendental, but still it is far from being a transcendental number. Now, if we substitute m equals to 1 here, then you will get this identity for zeta 3. Now, since right-hand side is transcendental, so therefore you can easily say that at least one of these two expressions must be transcendental. If not, if both of them are algebraic, then the sum of algebraic numbers will be algebraic, because algebraic numbers form a field. Okay, so Gun, Murthy, and Roth, they mentioned this Judelin type result. From large results, it's just a one line thing. At least one of these two expressions must be transcendental. Okay. And from this result, we proved that there exist infinitely many transcendental number in this set. Okay, so it's just, you have to prove that from each pair you will get one. So if we just show that these are all distinct numbers, so then you can immediately say that in this set infinitely many transcendental numbers will exist. But the problem, drawback of our result is like ball and revolt results, it was the set of all odd zeta values. But here we have only odd zeta values which are of the form zeta 4k plus 3 form, and this Lambert series are there. Okay, but one good thing is that like we are saying about transcendentality of these numbers, which is much more stronger than irrationality. Okay. Now let's see some known values of Lambert series. So from Ramanujan's formula, one can obtain this. The Lambert series is just a rational number, since B2M is rational. Bernoulli numbers are rational. Now again, from Ramanujan's identity, one can show that this Lambert series is just 1 by 24 minus 1 by 8 pi. So since pi is a transcendental, so therefore this quantity, this series is a transcendental number. Now again, like this is not quite easy. This one cannot obtain from Ramanujan's identity immediately. One needs a little effort to obtain this. This comes from the special values of Eisenstein series. Soon I'll mention that. Now you see gamma, a few years back, Yuri Nesterenko proved that pi, gamma 1 by 4 and e to the power pi, they are algebraically independent. And using the theory of modular form, he has proved that breakthrough result. And so therefore we can say that this Lambert series is a transcendental number. And the last identity comes from the here. If you substitute m equals to 3, then you will get basically this identity. So from these values, just I wanted to mention, because it's very difficult to predict this Lambert series, the algebraic nature of these Lambert series. Okay. Now let me talk about.
Excuse
Yes.
me, Vivek.
Yes.
I just had a question.
Yes, please.
Previously, you mentioned about your result. So, any quantitative versions were known, as in you said infinitely many transcendental, but like in ball revolve type.
No. Yeah, no, that's a very good question. Yeah, no, not quantitative results is no. Yeah.
You just know that there are.
Yes, exactly. But whereas ball and reverse results, they give that dimension, like
Dimension.
at least c times log n. So that's quite important. Yeah. Yeah, that's a good point.
Thank you.
Yeah. So now, are there any other questions? Okay. So now let me talk about Eisenstein series. Let k greater than or equals to 4 be an even integer, and z is any point in the upper half plane. Then this series is known as Eisenstein series. So where m and n are running in integer, except both are not simultaneous, it's 0. So it is an important example of modular form of weight k over the full modular group SL2Z. And one can prove that it satisfies this following Fourier series expansion. So here, this zeta k, the well-known Riemann zeta function at k. Okay. And this coefficient is sigma k is well-known divisor function. It's just sum is running over all the divisors of n, then this weight d to the power k. Yeah. Now let me mention Grosswald identity. In a series of papers, Grosswald studied Ramanujan's formula for odd zeta values, and he found this beautiful generalization. For any complex, for any z in the upper half plane, so it's immediately comes from Ramanujan's identity. At the beginning, I mentioned that Ramanujan's identity is true for any alpha, beta, both are positive real number. But that can be analytically continued to for any alpha with real part of alpha greater than 0, as well as for beta also real part of beta greater than 0. And then you change alpha and beta suitably in terms of z, then you get this expression. And where fkz is nothing but this series. Okay. Now one can easily see that when k is odd, negative integer less than or equals to -3, then this fkz is nothing but it is connected with the Eisenstein series z1 minus k comma z. Okay, so this is since k is less than or equals to -3, so 1 minus k is greater than or equals to 4, right? And since k is odd, so 1 minus k will be, so it is not exactly equals to this g1 minus, because you have to normalize Eisenstein series, okay? Then only you will get this thing. So you see, so fk is defined this series. So first you have to normalize this, then you have to remove the constant term, then you will get the fkz function. Okay. So just I wanted to say that this Ramanujan's formula is connected with the theory of modular form. And further, like Gun, Murthy and Roth in this paper, they studied this fkz function, transcendence values of this fkz. Fkz actually, it is an Eichler integral of Eisenstein series. So it has some integral representation also. Okay. So then in the same paper, Gun, Murthy, Roth defined Ramanujan's polynomial as this series, this this finite sum they defined as Ramanujan polynomial. And interestingly, Murthy, Wang and Smith, they proved that all the complex zeros of this Ramanujan polynomial, they lie on unit circle. And later, Mathilde Lalline and Matthew Rogers, they also studied similar Ramanujan type polynomial, and they also observed that there are similar polynomials which has also some kind of properties, like all the complex roots, It may have real roots also, but they may not lie on the unit circle. It's not necessary, but complex root will lie on the unit circle. And further, this work of Gun, Murthy, and Roth, further it was extended by Bruce Berndt and Armin Straub, okay, on this Eichler integral. Okay, so I hope I have convinced you that Ramanujan's formula for zeta 2m plus 1 is indeed connected with the theory of modular form. Okay, now let me talk about work of 3 Japanese mathematicians, Kanemitsu, Tanigawa, and Yoshimoto. So let H and N be fixed natural number with this restriction on H and N. Then for any positive real number, they studied this Lambert. This is a generalized Lambert series. Okay, so this Lambert series is equals to Px plus Sx, where Px is some term involving Riemann zeta function and gamma function. So no need to remember these terms. So just will remember that they have studied this Lambert series. And where Sx is also infinite series, complicated terms, which depends on the parity of n. When n is odd and when n is even, then it is something else. Okay. Now, surprisingly, when we see that Ramanujan's lost notebook, page 332, exactly Ramanujan wrote exactly same series which was studied by Kanemitsu, Tanigawa, and Yoshimoto. So here's the picture from Ramanujan's lost notebook. So here you see at the end of this page, okay, so it's not visible, I'm sure that. So let me, in the next slide, I'll write it properly. So last line, I mean the last line. Now, one more interesting fact is that in this page, you can see this cursor here. It is a formula for zeta half. So in the same page, Ramanujan wrote a formula for zeta half. And this is also the same Ramanujan's formula for zeta half, but in a different way he has written. Okay, now let me mention this series. Okay. Okay, so in his words, he has written, this is the thing, 1 to the power r by e to the power 1 to the power s times x, where x is a positive real number, and this series goes on. Where s is a positive integer and r minus s is any even integer. Whereas Kanemitsu, Tanigawa studied this series. Okay. Now, if you see, like, if you substitute s equals to capital N and r equals to n minus 2h, so r minus s is negative even integer. So Kanemitsu, Tanigawa studied. Ramanujan does not give any expression for this series. Okay. So yeah, one might think that the next page might be missing. So yeah, it may happen because Ramanujan's lost notebook is a collection of his loose paper. And this is the, like, I have seen this is the first instance, like usually Ramanujan always write left-hand side of an identity equals to right-hand side. But this is the first instance, like he has written this expression, that's it. Next page is totally different. So Ramanujan knew the importance of this series, otherwise why he would have written this series suddenly. So at this moment, we thought that since Ramanujan wrote that r minus s is any even integer, so I and Professor Dixit, we thought that we should try to extend the work of Kanemitsu, Tanigawa, and Yoshimoto. Okay, so here is the extension. Let n be any natural number and h be any integer. So no restriction here. Then we studied the same series, generalized Lambert series. Then we got that P1x plus Sx. So where Px plus this term, where Px and Sx that are exactly same as it was in the case of Kanemitsu, Tanigawa, and Yoshimoto. Now this extra finite sum involving Bernoulli numbers is coming. Now, at this moment, one might think that there might be some connection with Ramanujan's formula for odd zeta values. because in Ramanujan's formula for odd zeta values also there was a similar Bernoulli numbers were present. Okay. So indeed, we found a beautiful generalization of Ramanujan's formula for odd zeta values. So when let n be an odd positive integer and alpha beta both are positive real number with this condition, alpha times beta to the power n equals to pi to the power n plus 1. And then for any non-zero integer, this identity holds. Yes, of course, it may look a little complicated, but let me explain you. So if we substitute capital N equals to 1, then it will reduce to Ramanujan's formula for odd zeta values, because this zeta value will be zeta 2m plus 1 by 2. And this Lambert series, everything will get simplified. So this sum over j will reduce to only j equals to 0 tau. Now, the importance of this generalization is that Ramanujan's formula in the left-hand side and in the right-hand side, same odd zeta values was present. But now, because of this extra variable capital N, so when n is greater than capital N is greater than 1, we are able to connect two distinct odd zeta values from this formula. So that's the importance of this generalization. And this finite sum involving Bernoulli numbers, that is also getting generalized with this capital N variable. Okay, now let me quickly mention another joint work with Professor Dixit and Rajat Gupta.
Vivek,
yes.
One question was there in the chat.
Yes,
so
yes.
I didn't want to interrupt you, but
Yeah, no problem.
Anup Singha Roy was saying,
yes,
you can read it.
Yeah, is there any reason for considering Z upper in and Grosswald identity? Okay, yeah, will it be valid in the lower half plane? There will be some issues considering in lower half plane. Okay, that's a very good question. So just we have to see that mod of Q is less than 1 or I think if Z is in upper half plane, then only mod Q, like e to the power 2 pi I Z. If you take the mod of that, modulus of that, so just substitute Z equals to x plus IY. Okay, so then in the theory of modular form, the Fourier series expansion is valid like every time we consider Z is in the upper half plane. Okay, so then mod Q won't be less than 1. So then there will be problem in convergence. So that's why Z must be in the upper half plane. Okay. I hope your Anup your answer. Can you hear me, Anup?
Yes.
Yeah, answer got clear to you?
No, sir. Yeah, Eisenstein series is not convergent for a lower plane. You said, but I am not convinced with that.
Okay, like if you so
we know that Eisenstein series something.
So just wait. Like I is there. Yeah, e to the power 2n pi will come. I think yes. So x plus iy you are writing. Okay. So say like just wait. So let me show you. Let me go to that slide. Yeah. So here you see you when you are replacing Z, right? Any complex number. So it will be what? Y is your negative plus, then real part is e to the power 2 pi x, that is gone, minus 2 pi, yes, minus 2 pi ny, right? And now y is your negative again. So it is 2 pi I. So the whole like exponential will go to when n tends to infinity. So this exponential is going to infinity. And this has a polynomial growth. So this won't converge.
Yes, yeah. I got it.
Is that okay?
Yes.
The K can be anything because
K can be anything. K can be, but in this series, above series, K cannot, K would be greater than equals to 4. But in the equation 2, K can be anything. Yeah, that's the beauty. Yeah, it's a good question. Okay, now, any other questions?
Actually, I had one question.
Okay, so yes, Sumukha. I cannot hear you.
You have shown that Ramanujan identity. Hello, can you hear me?
Yes. Now I can hear you. Yeah.
Okay, I will write it in the chat box.
Okay. Yeah.
Okay,
Maybe I
like
can.
you have shown that. Okay.
Others, can you hear him?
I think there is some delay.
You can just continue and
Yeah.
Yeah,
So,
later at the end.
yeah, Sumukha, it will be nice if you write in the chat box. Then at the end, I'll try to answer that.
Yeah, I will do that.
Yeah, sure. Okay. Now let me quickly mention another joint work with Professor Dixit and Rajat Gupta and Rahul Kumar. So in the first generalization, we studied this Lambert series, and that can be written in terms of this line integral involving gamma function and product of this two Riemann zeta function. And then we thought that like Hurwitz zeta function is, as we know that Hurwitz zeta function is a natural generalization of Riemann zeta function, then we can try to extend this work. Okay. So, so in that case, the Lambert series will change this way. And so here in the right-hand side, this Riemann zeta function is getting replaced by. But the problem is
we are not seeing the slides. I mean, in the sense, I don't know whether it's only with me.
Okay.
Yeah, even we can't see it. Maybe you should.
Yeah, maybe
Yeah.
I'll share it once again.
Yeah, now we can see.
Okay, good. Thank you. Yeah. So, so as I was saying that this first we studied this generalized Lambert series. So that can be written in terms of this line integral involving gamma function and product of these two Riemann zeta function. And then as Hurwitz zeta function is a natural generalization of Riemann zeta function, then we thought that we can try to extend this our previous work. But the problem is like Hurwitz zeta function does not enjoy Euler product, whereas Ramanujan Riemann zeta function has a nice Euler product and it has a nice functional equation. Although like Hurwitz zeta function does has satisfy a functional equation, but it is not so symmetric. So that's why it was quite challenging to find proper generalization in the case of Hurwitz zeta function. So first, this Lambert series will get generalized in this way. And in that right-hand side, this line integral, it will be like this Riemann zeta function will get replaced by Hurwitz zeta function. Okay, then we got this two variable generalization of Ramanujan's formula. Let A is the that is the variable which was present in Hurwitz zeta function, and then n be odd positive integer and alpha beta be two positive real number with this condition. Then for any positive integer, so here it is not true for any integer, non-zero integer. So we were somehow we are not able to extend this result for negative integer. So there was a convergence issue. So, but the importance fact I'll mention, like at the beginning with the generalization with Professor Dixit, we have seen that it was giving us a relation between two distinct odd zeta values. But now, because of this extra variable small a, we are able to connect many odd zeta values at a single time. So soon I'll mention one corollary. Okay. So theorem is a little bit big. Okay. So here is the corollary, like substituting a and some a equals to half and n equals to something. Then you will get for nice, beautiful formula, which is relating zeta 3, zeta 5, zeta 7, zeta 9, and zeta 11. And all these big rational numbers are coming because of Bernoulli numbers. So that's the beauty of this generalization. Because of this extra variable a, we are able to connect many odd zeta values at a single time. Okay. Now onwards, I'll mention a joint work with Anusri. So I have just a few slides back, I have mentioned that to obtain first generalization of Ramanujan's formula, we studied this integral. Okay. Now, here, what we thought that what will happen if we replace this zeta s, first zeta s by zeta ks, and second zeta factor by zeta of s minus r. And there is a intersection between these two things when k and capital N both are same and r is equals to 0. And that means here in this above integral h should be n by 2. So in this case, they are coincident. There is an intersection. Otherwise, like the results from the previous generalization and results from this work is totally different. Okay. So this sigma z is this function, divisor function I have already mentioned. For any complex number, one can consider this divisor function. Now, in this project, we encounter these two new divisor function. So where the sum is running over, like it is not running over all the divisors. When k equals to 1, then it will run over all the divisors. Otherwise, it is running over the divisors which are of the form kth power. Then some weight is there. When k equals to 1, these two divisor function immediately reduce to sigma function. Okay, now let's see generating function for this divisor function. So it is well known that the generating function for sigma is nothing but sigma s times sigma, sorry, Riemann zeta, these two product of these two Riemann zeta function. And one can easily prove that the idea of this divisor function comes from this product of these two Riemann zeta function. This is not so difficult to prove. And this is valid only when real part of S is bigger than maximum of these two quantities. It's not an interval. It is maximum of 1 by k or 1 plus r. Yeah. And similarly, one can show that the generating function for this sk s divisor function is product of these two Riemann zeta function. Okay, now let me mention Maji function, which is an important special function. It's a generalization of many well-known functions. So let m and pq be okay, now for integer with this restriction, let us consider p plus q complex number such that ai minus bj is not a natural number. Then Maji function is defined this way. Okay, so defined by this line integral, where in the denominator as well as in the numerator gamma factors are there. And the vertical line integrals, which is going from minus I infinity to plus I infinity, it separates the poles of the factors, these factors, from the poles of this factor. And this integral converges if this condition holds. Okay. Result. So here, let k is greater than equals to 2 and even number, and r is any even integer. Okay. And this d and s, these two I have already defined. Then this identity holds. Okay. So first three terms are coming because of the residual terms. And here you see in the last term, this s, that skr, this divisor function is coming, and this Maji function is coming here. Okay, so I'll in the next slide I will mention what is meant by this double dash. Okay, so double dash means the summation runs from this minus of k minus 1 to with the difference of 2. It is running not over like all integers. It's running from minus of k minus 1 to k minus 1, but with difference 2. Okay, and xj is some quantity which depends on n, k, and x. And r, this is a residue at 1 plus r, so which will vary. When r is positive, then it is this quantity, and when r is negative, then it is this quantity. Now, immediate corollary of our result is this: letting k equals to 2 and r equals to 0 in our previous theorem, and you have to do, you have to simplify a lot. then we obtain this Ramanujan's beautiful formula for zeta half. Okay, which I have already mentioned that this formula is present on the same page 332, like from where we got, we have seen that series expansion. Now, one may wonder that what is the importance of this kind of series? Okay, now if we recall that Euler's formula for zeta 2m, like that identity immediately tells us that all even zeta values are transcendental. Now, to know, like one may ask the same question, whether zeta half is algebraic or transcendental. I think it is still not known. So to answer those type of question, like if we substitute alpha equals to pi and beta equals to 4 pi square, then this series will get simplified. And then one requires to study this kind of Lambert series. So if we know the behavior of like algebraic nature of this kind of Lambert series, then it might be helpful to know about zeta half. Okay. Because zeta half is a quantity, if you substitute in the functional equation, you won't get like much information, because if you substitute s equals to half, then 1 minus s is also half. Okay, so for zeta half, like to explicitly evaluate zeta half, this kind of series expansion is important. Okay, now another corollary of our result is that if we substitute r equals to 0 and if you keep k is any even integer, then we obtain this formula of Wigert. So from to derive this formula also one requires a little bit effort. So here you see gamma 1 by k is also coming and zeta 1 by k. Like but this is a formula for zeta 1 by 4, zeta 1 by 6, that kind of thing. So one might wonder that whether there exists a formula for zeta 1 by 3 or zeta 1 by 5. So that I'll mention at the end. Okay, so let me quickly go through the proof. So first we write this series in terms of this line integral. Then to evaluate this line integral, we choose a contour in such a way so that the poles of this integrand function lie inside the contour. And the line segment, these are the line segments of the contour. Where lambda, you have to choose a little cleverly that it should be maximum of 0 or minus r. Since r is any integer, so r can be positive as well as r can be negative. And t is some large positive real number. Okay. Now let's see the poles of the integrand function. We know that the gamma function has simple poles at s equals to 0 and all the negative integers. But the poles at negative integers, they are getting cancelled by the zeros of zeta ks, because we are dealing with k even. And we know that Riemann zeta function has trivial zeros at negative even integer. Okay, so that's why all these poles at negative integers, they will get cancelled by the zeros of zeta ks. So thus the only poles, simple poles of the integrand function will be at s because of this gamma s, and because of this zeta ks, there will be one simple pole at 1 by k, and because of this zeta factor, it will be one simple pole at 1 plus r. But there is one point is that because since r can be negative integer, so 1 plus r, when r is negative, then 1 plus r can be also negative integer. So in that case, it may look like, it seems like 1 plus r is a pole of order 2, because of this gamma factor also will have a pole at 1 plus r if it is a negative. But zeta ks will have a 0 at 1 plus, since k is even. Okay, so that's why 1 plus r will remain as a simple pole, since we are dealing with k even. So that's one. Okay, so one can easily calculate these residual terms, so I'm not going in that details. And using Stirling's formula for gamma s and a bound for Riemann zeta function, one can show that both of the horizontal integrals, they will vanish as t tends to infinity. Now letting t tends to infinity in the above, you will get this. Now the main aim, the main difficult part is that, like, to evaluate this left vertical integral. So that is the challenging part. Okay. So let's call this left vertical integral as B, which depends on KR. So now, first we use the asymmetric form of the functional equation. So at the beginning, first slide, I have mentioned the symmetric form, and this asymmetric form can be obtained easily from that. So you use this functional equation twice, and then a little bit change of variable is required to get in this form. Then since K and R both even, then using simple trigonometric identity, one can simplify further this to sine function. And further simplifying, one can obtain this expression, where we can see the 2 gamma function, and in the denominator also 1 gamma function. Now, interestingly, here at this point, like real part of S is like we are integrating 1 on the line 1 plus lambda. Okay. Now here we can observe that the real part of S plus R and the real part of argument of this Riemann zeta both are greater than 1. So that can be, one can verify. And here you require that lambda, as we have chosen that lambda is bigger than maximum of this, then only this will work. And therefore we can write in terms of series expansion, and then we interchange the summation and integration to get in this form. Okay, so here one requires to use this lemma. Okay. So once you use this lemma, then you get this form. And after that, you have to use multiplication formula for gamma function, okay, to simplify further. And at the end, you can write like in terms of Maji function. So here also, to write, before writing Maji in terms of Maji function, one requires that all the conditions of the Maji function is satisfying or not. And at the end, still one requires to show that whether the series, this equation 31 converges or not. And for that, again, you have to use Stalin's formula for gamma function. You have to use the bounds for this Maji function to show that this infinite series is indeed convergent. So that completes the proof. Okay, now I'll mention another result. So K is when K is even and R is odd. So first result was K is even and R is even. Now we are considering K is even and R is odd. But here this identity is not true when it's not valid when R equals to -1, because in that case a zeta 1 will come, and zeta function has a pole at is equals to 1. So therefore, but for R equals to -1, you have to do it separately. We indeed mentioned one result, got a result for R equals to -1. So it's almost similar, but there is a slight changes there. So interestingly, if we put K equals to 2 and R equals to 1, then we got a new identity for zeta at -half. Yeah. So this is the, if we substitute K equals to 2 and R equals to 1 in the above result, in the previous result, we get this. And so this identity we have written in like in a similar form to Ramanujan's formula for zeta half. So here you can see that this expression is almost same as it was in the case of Ramanujan's formula for zeta half. Okay. And this pi to the power 4 by 90 is zeta 4 basically. So it's a little bit complicated than Ramanujan's formula for zeta half. Okay. Now another interesting part, when K and R both odd. Okay. So in that case, in this case also, like it is not valid when R is -1. So for R equals to -1, you have to do it separately. And in that case also we get like a generalization of transformation formula for a logarithmic of a Dedekind eta function. So that is the case when you substitute R equals to -1. Okay. Now here in this case, this one more extra term, this R is capital R I have written. Otherwise, this residual term is almost same. And this infinite series, this is also almost same. But this extra term R is coming. Okay. Now let's see what is this R. So this R, when small r is bigger than equals to 1, then this capital R residual term will be 0. And when small r is less than equals to -3, then it is a finite sum involving Bernoulli numbers. Okay. Now again, once you see this kind of sum, then you might wonder that there might be a connection with Ramanujan's formula for odd zeta values. Yes, indeed, we will obtain Ramanujan's formula for odd zeta values. So this is the another generalization of Ramanujan's formula for odd zeta values. So here k be an odd integer and m be a positive integer. So this identity also one can write for any m is a non-zero integer. So in that case, when m is a negative, so this finite sum won't be there. Otherwise, this is also valid for negative integer also. Okay. So this, now to obtain, now let me say one important thing. So in the generalization with Professor Dixit, we connected two distinct odd zeta values when capital N was greater than 1. Now, in this generalization, we are able to connect two distinct, when k is greater than 1, we are able to connect two distinct odd zeta values plus one odd zeta values at rational argument because of this k terms. So now that was not in the previous case, but from the previous generalization, we won't be able to derive this generalization, and neither from this generalization, we won't be able to our previous generalization. Okay. So these two are in a different direction. But the complicated part is that this Maji function still remains. So, okay, so recovering to recover Ramanujan's formula, you have to just substitute k equals to 1. Then you do little bit simplification, and so this d function reduced to sigma function, and both of them, and then you use this Maji. As I said, that Maji function is a generalization of exponential function. In particular, it gives. So you have to use this identity. Yeah, then like at the end, you have to use Euler's formula for zeta 2m plus even values. And yeah, so then you do a little bit simplification and to get Ramanujan's formula for odd zeta values. Okay, so I'll end with within 1 minute. Yeah. So, so basically, together with Professor Dixit, we studied this series where n minus r was any even integer. Okay, we have we wanted to study, that is in future, we want to study when n minus r is odd, then what will happen. So that is, that in that case also we'll get something interesting. So in this work, we have studied a variant of the above integral, as I said, that this zeta s, we have replaced this. Okay, but here, like one case we haven't studied, like when k is odd and r is even. Okay, so that case, when k is odd and r is even, so in that case, also integrand function will encounter infinitely manifold. So till now, whatever we have done, so every time it was finitely manifold. Okay. So in this case, infinitely manifold, and the poles will be at negative odd integer. So in future we are planning. So with this, here are the few references. Yeah, one important thing I'd like to mention, Bruce Bernd actually once, he studied a generalized Eisenstein series, and from there he was able to derive Euler's formula for zeta 2m as well as Ramanujan's formula for zeta 2m plus 1. So they are the branches of a bigger tree. Okay, it's not that they are not connected. So there is a higher theory where connects Euler's formula for zeta 2m as well as Ramanujan's formula for zeta 2m. Okay. So these are the papers. Yeah. So this is the paper of Kahneman. So with this, thank you. If you have any questions, please.
Thank you very much, Vivek, for a very nice talk. The floor is open for questions, if any. I think Sumukha has one question already written in the chat box, so you can. You want me to read it? Or?
Yeah, you have shown identity, which from that we can see some relation of Ramanujan's identity with Eisenstein series for two. Any result something similar to a higher level Eisenstein series? Okay, so I feel that there is a in that direction, like the work of Gunmurti Roth and then the work of like Bruce Bund and Armin Stroff, that also generalized in that direction. Like they connected with Eichler integral, like mainly Bruce Bund and Armin Stroff, they have done for higher level. Yes, I'm sure that a level for level 4, they have connected with. I think Professor Dixit, you can. I think they have connected some thing. Eichler integral. They have studied something. Yeah.
Right. And I mean, I did not know whether Smuka was meaning this higher level as in the sense of this n, like with our generalization of Ramanujan's formula. So if that is the case, then we yet do not know what the role n plays.
Yeah. So our generalization, what is playing with the modular form, that we till now we don't know. But there are certain Eichler integral with Eisenstein series, like Eichler integral with Eisenstein series of higher order, that has been studied, and transcendence values of Eichler integral in that direction. So I think better it will be nice to see the work of Bruce Bund and Armin Stroff. So
even in our formula, if we have that capital N as it is, but we specialize on the values of M, that is when M is positive odd or negative odd, that way we can get formulas which will reduce to transformation formulas for Eisenstein series when capital N equal to 1, but we don't know here how that fits into the broader picture of modular forms.
Yes.
So in that.
Okay. Thanks.
Okay. In that regard, Vivek, I had one more question. Do you have any information about K, the K that you have in your formula?
Yeah, actually, yeah, I don't know. Actually, that is the yeah. There might be some connection. Yeah, we have to see further. Yeah.
Okay.
Like that was one interesting fact we observed, that because of this K, we are able to connect two distinct odd zeta values and one odd zeta values at rational argument. So that was one nice thing, which was not coming from our previous generalization. So that is one good thing we observed. Yeah.
Okay. Any other questions? Yeah, if not, may I request everyone to unmute and then clap for the speaker?
I had a question, sir.
Oh, sure. Yeah.
Hello. Yeah. Hello, Dr. Maji. So there was a point where you said that Vadim Zurlin had the best result, in which, like, you said that at least one of zeta 5, zeta 7, zeta 9, or zeta 11 is irrational, right? So my question is, what was the difficulty in pointing out exactly which one is irrational? Like he said that at least one is. Yeah. So my question is always for.
Yeah, like when you are saying like the field like generated by zeta 5, zeta 7, zeta 9, so the degree of the extension is supposed, like, I don't know exactly the region he used linear forms. Okay, but if you say the degree of the extension is greater than 1, okay, but which one is irrational, that you cannot say. Okay. The degree of the extension is greater than 1, that you can say, but you don't know which is one is.
Okay. Thank you.
Yeah, that kind of difficulty might be there, but I'm not quite sure. We have to see. Actually, I was trying to read his paper, but it was in Russian language, so I couldn't. Yeah, but we have.
Okay.
But he has wrote another paper, like that is in English. So like you can see there, a number of odd zeta values is more. Okay, from I think 13 or something. So there you can see, if you are interested, you can see that paper. Yeah.
Okay, thank you.
Thank you.
Any further questions? Okay, if not, may I request